Now I'm going to explain diffraction. What is diffraction in details? Diffraction is this is the definition of diffraction. Divergence or bending of a light, not only light, all waves, all types of waves, from their initial direction is called diffraction. Divergence. Divergence 1, divergence 2, divergence 3. What's those things? You know that divergence.
Insert.
Yeah, okay. Divergence is, in fact, there are more than different characteristics of person. There is. Some are different characteristics of other person. Yeah. In fact, they are not just one prototype. Yeah, it's in fact saying that don't think that light is follow straight line path. It diverges. Yeah, it bends. So divergence, banding. Sometimes for divergence is also we say about angle of deviation. Deviation, also you can say deviation. Divergence, deviation, banding of light, or not only light, all waves from the initial direction is called diffraction. This is a good example. Jim is talking behind the door. Jack is behind the wall. Jack cannot see the Jim. She cannot know Jack is there because the wall is blocking them, their vision. However, Jim is unaware that sound can bend. Jack can hear what Jim is talking about. So, this is the proof that you can hear someone who is talking around the corner, but you cannot see that person. Because sound waves are able to bend around the corner. However, light is not bending around the corner. But both are waves. Sound is a wave. Light is also a wave. However, sound has a very long wavelength. Light has a very, very short wavelength. Then this can give you an information. So diffraction becomes noticeable for waves of long wavelength. As wavelength increases, diffraction becomes more noticeable. As wavelength decreases, diffraction becomes less noticeable. Because light has a very small wavelength compared to the sound. Okay? Then let's repeat again. Longer wavelength, as wavelength gets longer and longer, diffraction becomes more noticeable. As wavelength gets shorter and shorter, diffraction becomes less noticeable. And this is the diffraction of water waves. Water waves also diffract. You see there's an opening? There's an opening? Normally, incoming water waves are flat. After they pass, they start to bend. Normally, if no bending, this water wave must go between these regions. It should continue that way. But they start to bending. Normally, they go the places where normally they don't go. So this is also a bending. These waves are bending as they are passing through this opening. Light has a very short wavelength, so that's why we have to do something to make it observable. Diffraction in light occurs when light passes. And in three places we are going to see diffraction in light. One of them is light will pass through a slit. We will observe diffraction.
Yeah.
We will study this in details.
Yeah.
And also, as light passes around obstacles, this obstacle can be a pen, but I put pen. When the light passes around this pen, so it diffracts, bends. And also, by sharp edges. Now, what does it mean? At the end of this slide, I am going to explain this title. But basically, now we are going to study this part, through a small opening. So diffraction of light through a very narrow opening, first we are going to study. If opening is quite wide, when I was talking quite wide, 1 millimeter, 1 millimeter is not quite wide in fact. But compared to wavelength of the light, it's wide. It's too wide. It's nanometer you are measuring the wavelength, but 1 millimeter is maybe how many? 10 to the power 10 times greater than that. Negative, positive signal greater than, yeah.
Yes.
So opening is quite wide. In this case, when you put a light source in here and then there's a slit, you are going to observe that on the screen you are going to see just one clearly marked edge rectangle. Just single, bright region. You are going to observe that. All other parts is going to be shallow. However, if the opening gets narrower and narrower, if you make this opening narrower and narrower, you will observe something very interesting. This is what we see in here, if it is white. So, with a slit width. But as slit width decreases, this region, which is bright, starting to be bluey from here to there. So, when slit width changes from D to 0.8D, then changes to 0.2D. When we change to 0.2D, we are observing something very similar to an interference pattern. You see that? Bright, dark, bright, and so on. But how this happens? Normally, until interference, model of the light was particle model. Particle model cannot explain that, because when a particle is moving in free space, it doesn't change direction. Why should it change? If you don't apply a force on it. Particle does not change direction. So if the light is particle, this cannot happen. Then they started thinking, okay, then particle model is not enough to explain this.
What do you mean by particle?
Particle means, for example, I drop this. So if I drop this, it will go a straight line, right? If the light is just like, because light is particles, particles must move on a straight line. If they move in a straight line, so this must happen only. Yeah, the particles which are coming through the slits will pass and then come in here, eliminating here. Other particles pass and eliminating here. You are going to see just a rectangle, illuminated region.
Yeah.
But now we see this is not just single rectangle. There are other parts as well. This tells you that particle model is not valid for light.
So it changes there.
Yeah, because direction changes. Then, what should they do? They will turn back to the era of Isaac Newton. Isaac Newton is the first scientist who said that light is in the form of particle, because he's a very big influence on the scientific world. They said okay, but at the same time, one scientist say an opposite thing. At the same time, they live at the same time. Christian Huygens, he said that light is in the form of wave. Nobody cared what he said. When this happens, this is observed, then they started to look back. Okay, at the time of Isaac Newton, someone else said something else. Let's try this model, Huygens model. And by Huygens model, yes, we can explain this event. Then what does it mean? Light is also wave. Now, we are going to study Huygens model. I will explain Huygens model how this model explains the pattern on the screen and the bending of the light while it's passing through a slit. If light from a single slit, it is a single slit. Normally single slit, according to section 1, cannot produce an interference pattern. We need at least two slits. Or you observe interference pattern by two slits. If light from single slit forms an interference pattern on a screen, then it can be predicted that there must be tiny light sources within the slit. And inside this slit, we are going to assume that there are tiny, multiple light sources. This is what Christian Huygens said centuries ago. According to Huygens' model, within this slit there must be tiny light sources. I put 1, 2, 3, 4 sources in here. These tiny light sources interfere on the screen just like diffraction grating does. So, screen appears at some region bright, at some region dark, some region bright, some region dark. Now, I'm going to explain the Huygens Principle in detail because it's the Mr. Exam question. According to Huygens Principle, each portion of the slit, each part of the slit acts as a source of waves. This is slit from here to there. I located here 5 tiny light sources. You can put 10, 20. This is not visible to us. This is a model. So I put 1, 2, 3, 4, 5 light sources. And according to this model, each source produces its own wave. Yani first tiny light source produces its own wave. Second tiny light source produces its own wave. Third produces its own wave. Each of them Huygens set wavelet. Wavelet. Yani this is a wavelet. This is second wavelet. Another wavelet. Another wavelet. Another wavelet. And as waves travel, of course this wavelet will expand. You know that as wave travels, the size gets bigger and bigger, larger and larger. So look at now. This wavelet was small, but after some time, it becomes very large. What happened? Normally, according to classical theory, this light must pass between these 2 lines. But now it's extended. It went to left. This side goes to...
So it deviates.
It deviates according to wave model. If you don't use wave model, it cannot deviate. Wave model explains that. It starts to deviate. After some time, of course, these wavelets will be much larger. So their size is going to be something like this. So as wave travels, it starts to deviate to the right and to the left. Okay. As a result, light deviates from the straight line path and enters the region that would otherwise be shadowed. Normally, all this region must be normally illuminated. Other parts should be shadowed, dark. But because of deviation, these regions are also illuminated. As Christian Huygens model explained that why here is bright. Why here is bright. Next step is why we see interference pattern. Now we will talk about this. But this model is the Ministry Exam question, Christian Huygens model. Now turn the Ministry Exam question pages. Let's check how they ask this in Ministry. Question number 4, I think.
All points on the wavefront of the
Yes. All the points on a wavefront of a plane wave can be treated as a point source, whereas each of these point source produces a circular and spherical secondary wave, which is called wavelength. This principle is named as... Yes, this is Ministry Exam question. We have to know this. And basically, this statement is explaining what Huygens Principle is. And asking you what is this. Now we are going to try to explain why some regions are bright, why some regions are dark. Okay, according to the screen, when we look at the screen, we see that center is the brightest and also widest. When waves arrive at the center of the screen, they form a brightest fringe. At the wavelength screen's midpoint, all the rays from the slit travels the same distance. Yani, wave from first source, wave from second source, wave from third source. All they travel equal distances. Okay, are they in phase in here?
Yes.
When they travel equal distances, will they be in phase there?
Yes.
If they are in phase,
Then
constructive interference takes place. That's why center is the brightest. All sources constructively interfere.
at the
So,
center.
yeah, at the center. Waves arrive at the center in phase. All of these waves coming from those tiny light sources arrive at the center in phase. All tiny light sources constructively interfere and a very bright fringe appears at the center. Now, what about dark? How should happen? How this becomes dark? Now we will try to explain that. If this point is dark, if the light waves are coming from these sources must arrive at this point out of phase. But how Huygens model help us? Now we will try to get it. If we divide this tiny light source into 2 portions, 2 halves, upper half, lower half. Upper half is this. Lower half is that. Upper half travels a shorter distance than lower half. Yani one waves from one half travels longer distance than waves from other half. If wave from the lower half travels lambda over 2 longer than wave from upper half, what happens? So destructive interference takes place. Then that point appears dark. So upper half and lower half of the tiny light sources must be out of the phase to make destructive interference, to make dark. So then we can say that lower half travels lambda over 2 extra distance than upper half. Then this point appears dark. But there's other bright fringes. But these bright fringes are less intense than center. Center is the brightest. Now question, brightness is determined by what?
Constructive interference.
Number of sources. Number of sources which constructively interfere. If all sources are constructively interfere, it's brightest. But if number of sources which constructively interfere decreases, so brightness must decrease. This is a key information. So then, which means at this point and that point, number of sources which are constructively interfere is decreasing. I can get this result from this pattern. Now, keep this in your mind. So now I'm going to study this part now. It is dimmer than center. When waves arrive at a point which appears less bright, dimmer than central, bright fringe, I can conclude that less number of tiny light sources must constructively interfere compared to center. Yani at the center all 5 constructively interfere, and then it's the brightest. But in here must be less than 5, correct? Then how Huygens model can help me? This time we are going to divide these tiny light sources into three portions. One portion, other portion, third portion. If first portion and second portion out of the phase in here, yani if second portion travels lambda over 2 longer than first portion, these 2 portions will cancel each other. What about third portion? It remains uncancelled. What does uncancelled mean? They are going to constructively interfere in here. If they constructively interfere, what will happen? Right. But how many sources constructively interfere now? 2. Compared to center? Center 5. Yeah. That was the brightest. But now only 2. And less number of the source constructively interfere. That's why this point appears again bright, however, dimmer than the center. Another dark. There's one more dark, huh? So dark means complete cancellation again. This time, for this dark, we are going to divide this tiny light source into 4 portions. 4 portions. 1 and 3 will cancel, 2 and 4 will cancel. Then we divide them. Again, complete cancellation. Yeah, I'm going to divide these tiny light sources. Now, 4 parts, 4 portions. 1, 2, 3, 4. 1 first portion, third portion, out of phase. 2 and 4, out of phase. So they cancel each other. That's why this point again appears dark. What about this point? It is much dimmer than this one. Yani number of tiny light sources is constructed decrease again. Yeah. This time we are going to divide, we can predict. This slit into
5.
5. Yes, you're right, 5. 5. Then we divide into 5. 1, 3, destructive interfere. 2, 4, destructive interfere. Which one is left?
5.
5th is left. But as you divide them into portions, number of source decreases. That's why this point appears much dimmer compared to the second one. It goes on that way. And always you are dividing this slit into portions. And as you divide them into portions, of course, number of the source, which is constructed interfere, decreases. That's why the brightness also decreases. Okay, and when we look at the pattern, we see that center is brightest. central bright fringe is brightest. So we're a single slit diffraction pattern. Sometimes you notice a diffraction pattern because first light diffracts, after that interfere. And there are in here two things happens. In fact, in interference two things always happens. First one, as light passes through the slits, they diffract. Diffraction occurs always. In single slit experiment or double slit experiment. When we are talking about double slit experiment, we didn't talk about this. But in fact, it happens there as well. Diffraction occurs every time when light passes through slits. So first light diffracts, after that on the screen, interfere. So a single slit diffraction pattern consists of intense central band. Yani center is very intense, you see. Intense is very big, high. Central bright fringe, it's called central bright fringe. You know why central called? It's at the center of the screen. And one more thing, look at the size of them. Center size is twice. Twice the size of the first one. Twice as wide as the next brightest fringe. And also quite brighter than others. And center, quite brighter than other bright fringes. But there are some less intense secondary bands as you see. First bright, second bright, but they are less intense than the center. Less intense secondary bright fringes or secondary bright bands, which is called secondary bright fringe. Secondary bright fringe, secondary bright. It doesn't mean second bright fringe. Secondary is, primary is the center, which is the brightest and then widest. Other bright fringes are called secondary bright fringes. Of course, they have orders as well, but we don't talk about orders in here. These are called secondary bright fringes. Their intensity is less, and they are also narrower compared to the central bright fringe. Between these two bright fringes, there is a dark fringe. Of course, a series of dark bands. Dark fringe also exists between these bright fringes. This is a single slit diffraction pattern or single slit interference pattern. And remember, when I was first started diffraction, I said that diffraction happens in three places. One of them is when they pass through small openings, around sharp edges, and while passing around some barriers. Now, I need to explain the second part. Diffraction occurs around edges of all objects. Diffraction occurs around the edge of all objects. But some are more noticeable, some are less noticeable. For example, this one is diffraction. Normally not visible to your eyes, can be detectable only by using magnifiers. If you use a magnifier, you can see that. The pattern consists of a shadow. You see, this is the diffraction pattern around a coin. When the coin is illuminated, of course, shadow is coin's shadow. But around this shadow, you are going to see lines. You see that? Some lines. Bright, dark, bright, dark, bright, dark circles. This is also because of the diffraction. So, the pattern consists of shadow, yes. After shadow, a series of bright and dark bands. Bright, dark, and so on. That continue to the shadow edge. Also, this is a razor blade, sharp edge. Razor, you know razor blade?
Yes.
Look at that. When the razor blade is illuminated by blue light, you see that normally this is where the razor blade's shadow ends. But after that, still you see bright, dark lines. This is also because of diffraction. If the object is large compared with the wavelength of the light, this diffraction happens, but not visible to your eyes. That's why you should use magnifiers to see that. So, razor blade is so large compared to wavelength of the light. The wavelength of the light is measured by nanometers. So, razor blade is centimeters. So, it's very large compared. That's why you cannot see it by naked eye. You should use a magnifier to see these patterns. Okay, some conceptual challenge questions and then some sectional questions. We are going to finish with this section. One of them is about the star, photographs of a star. This is the photograph of a star. Photographs of stars always shows spikes. Spike. Maybe you are familiar with it because of the coronavirus, huh? Spike protein. Normally, coronavirus is a spherical shape, but around the sphere there are some. Normally, picture of a star must be a bright region, yes, but around these bright regions, some you see that some circles, dark and bright and the dark and bright. So these are called spikes. Photographs of stars always show spikes extending from the stars, as you see, it's extending outward. Given that aperture of the camera's rectangular shutter, every camera has a shutter, you know that, has a straight edges, yani clearly marked edges. Explain how diffraction accounts for spikes. Explain part is not a mystery option, of course, but the question can be this. Why there are spikes around this picture? Because of diffraction. Because diffraction makes bright, dark, bright, dark, bright, dark circles. And these circles are producing a spike around this bright region. Now, the edge of the camera shutter diffracts the light and causing secondary maxima. What is secondary maxima? We learned that. This is centered as a primary, which is the bright fringe, one central bright, but the others are secondary maxima, and this secondary maxima appears on the sides of the star's image, as you see. These maxima give appearance of the light spikes around the star. Question number 2. Visible light waves are not observed diffracting around the buildings. If it is like this, I should be able to see somebody behind the door. Can you see? Visible light waves are not observed diffracting around the buildings or other obstacles. However, radio waves can be detected around the buildings. Yeah, when you go behind the building, can you listen to radio?
Yes.
So how can that building block this radiation?
Because
they are diffracting. They are changing direction, bending, and arriving where you are. But why? Why radio waves can bend, but light cannot? It's about the wavelength. Remember section question at the end of the section 1. Radio waves are, that radio waves with 3.25 meter. A light, not a meter. So even not comparable. Then we can say that longer wavelength light or waves, for longer wavelength waves, more noticeable. Diffraction is more noticeable. For shorter wavelength waves, less noticeable. That's why diffraction for the light is not noticeable for us if you don't make an experiment with single slit or something like this. But radio waves, sound waves, water waves can easily diffract around obstacles. 3 more questions we are going to answer. These are the sectional questions. Describe the change in the width of the central maximum of single slit diffraction pattern as width of the slit may be smaller. Think opposite. If it is wider, we are going to see only just one clearly marked rectangle. Remember that example?
Yes.
But as it gets narrower and narrower, what happened? It started to diffracting. Yani size of the central maximum is this time increasing because of the diffraction. Yani when you are making this slit narrower and narrower, diffraction becomes more noticeable. That's why central band starts being wider. Mathematically, you can use this equation. But instead of t, you are going to write width of the slit. In fact, we have such an equation in the physics, but in your book, this equation is not given. As width increases, theta increases. As width decreases, theta increases, which tells you that width of the central maximum increases when you make width of the slit decreases. Yeah, width of the slit decreases, slit gets narrower and narrower, but central maximum becomes wider and wider, inverse changing there. Question number 3. Which object would produce most distinct diffraction pattern? This is an exam question. An apple, a pencil, or a human hair. What do you
Human
think?
hair.
Human hair, of course, because its size is small. Another thing. As size of the object gets smaller and smaller, diffraction becomes more noticeable. Let me repeat again, this is one another important thing. As size of the object gets smaller and smaller, diffraction becomes more noticeable, more distinct. That's why human hair has a smaller size compared to apple and pencil leaf.
Yes.
That's why it will be, the diffraction will be most distinct for human hair.
Distinct.
Distinct means more noticeable. More noticeable. Distinct means that. Question 4, in fact, you can answer very easily. Which color diffracts the most? We know that because depending on this equation, greater lambda, more diffraction. So would orange light or blue light produce a wider diffraction pattern? Of course, orange has a longer wavelength than blue. That's why it diffracts the most. That's why its pattern is going to be wider compared to blue light.